In mathematics and theoretical physics, the idea of a representation of a Lie group plays an important role in the study of continuous symmetry. A great deal is known about such representations, a basic tool in their study being the use of the corresponding infinitesimal representations of Lie algebras. The physics literature sometimes passes over the distinction between Lie groups and Lie algebras. Representations on a complex finite-dimensional vector space. Let us first discuss representations acting on finite-dimensional complex vector spaces. A representation of a Lie group G on a finite-dimensional complex vector space V is a smooth group homomorphism psi GAUT from G to the automorphism group of V. For n-dimensional V, the automorphism group of V is identified with a subset of the complex square matrices of order n. The automorphism group of V is given the structure of a smooth manifold using this identification. The condition that psi is smooth, in the definition above, means that psi is a smooth map from the smooth manifold G to the smooth manifold AUT. If a basis for the complex vector space V is chosen, the representation can be expressed as a homomorphism into general linear group GL. This is known as a matrix representation. Representations on a finite-dimensional vector space over an arbitrary field. A representation of a Lie group G on a vector space V is a smooth group homomorphism GAUT from G to the automorphism group of V. If a basis for the vector space V is chosen, the representation can be expressed as a homomorphism into general linear group GL. This is known as a matrix representation. Two representations of G on vector spaces V, W are equivalent if they have the same matrix representations with respect to some choices of bases for V and W. On the Lie algebra level, there is a corresponding linear mapping from the Lie algebra of G to end, preserving the Lie bracket. See representation of Lie algebras for the Lie algebra theory. If the homomorphism is in fact a monomorphism, the representation is said to be faithful. A unitary representation is defined in the same way, except that G maps to unitary matrices. The Lie algebra will then map to skew Hermitian matrices. If G is a compact Lie group, every finite-dimensional representation is equivalent to a unitary one. Representations on Hilbert spaces. A representation of a Lie group G on a complex Hilbert space V is a group homomorphism psi GB from G to B. The group of bounded linear operators of V which have a bounded inverse, such that the map G times V given by psi V is continuous. This definition can handle representations on infinite-dimensional Hilbert spaces. Such representations can be found in e.g. quantum mechanics, but also in Fourier analysis as shown in the following example. Let G equals R, and let the complex Hilbert space V be L2. We define the representation psi RB by psi F. See also Weiner's classification for representations of the Poincare group. Classification. If G is a semi-simple group, its finite-dimensional representations can be decomposed as direct sums of irreducible representations. The irreducibles are indexed by highest weight. The allowable highest weights satisfy a suitable positivity condition. In particular, there exists a set of fundamental weights, indexed by the vertices of the Dynkin diagram of G, such that dominant weights are simply non-negative integer linear combinations of the fundamental weights. The characters of the irreducible representations are given by the WEYL character formula. If G is a commutative Lie group, then its irreducible representations are simply the continuous characters of G. See Pontryagin duality for this case. A quotient representation is a quotient module of the group ring. Formulaic examples. Let FQ be a finite field of order Q and characteristic P. Let G be a finite group of Lie type, that is, G is the FQ rational points of a connected reductive group G defined over FQ. For example, if n is a positive integer GL and SL are finite groups of Lie type, let, where n is the n times n identity matrix, let then SP is a symplectic group of rank n and is a finite group of Lie type. For G equals GL or SL, the standard Borel subgroup B of G is the subgroup of G consisting of the upper triangular elements in G. A standard parabolic subgroup of G is a subgroup of G which contains the standard Borel subgroup B. If P is a standard parabolic subgroup of GL, then there exists a partition of N such that where has the form and where denotes arbitrary entries in